Oh, I see a Chris North.
Well, yes, there's a Chris North here. So we have a Director of Public Engagement for Cardiff University's Gravity Exploration Institute, our good friend Dr. Chris North. How's lockdown treating you, Chris?
Lockdown is not too bad. It's a bit odd not being in work, and it's a little bit hectic trying to work from home with the family and so on. I've actually sort of taken this week off as holiday. I was going to do it anyway. The intention was to be with family in other places, but that obviously hasn't come to pass.
Yeah,
so,
I was supposed to be in New York on Friday, as in, well, tomorrow.
Yeah, I wasn't going to go that far, but yeah. So it means that I'm a bit of time in the garden, which the weather is good. I'm grateful for having the garden to be able to send the kids out into and be in as well. Maybe lounge around for a bit. Read a book or that kind of thing.
I suppose it's not one of those things where you think, oh, damn it, the timing's really bad to take time off work because we don't know how long this is going to go on for, and people are going to lose leave at the end of the year anyway, aren't they?
Well, yeah, and we're being encouraged. I mean, a lot of employers and Cardiff University is no different. Is encouraging people to, not to cancel their leave for two reasons. One, I think, is that it's good to actually take time off, work and have a break, and the second reason is that it's good to not use up all your or not save up all your leave and then find you can't use it later.
Yeah,
exactly.
So Jed, I'll pass over to you.
Yeah, so we'll do some questions if that's all right with you.
It's fine by me.
First question comes from Father North, which when this question came in, I was like, "That's it. We got to do this one for Chris. Like, we can't not get Chris to answer his own dad's question."
You know, you can WhatsApp me, right?
Well, apparently he doesn't know that he can WhatsApp you because he asks his questions to us instead. But anyway, so Father North asks, why are astronomers so sure that Muamma and Borisov are from outside the solar system? If the objects were one half of a binary pair, somewhere in the Oort cloud, for example, then perturbed by a third, couldn't it be thrown towards the sun while the other was ejected at a greater than escape velocity? I mean, would more than one counter be required to give it the required velocity? So I guess the crux of the question is, how do we know that they are from outside of the solar system?
Yeah, I mean, this is a good question actually. So the reason that these two objects, so Oumuamua and Borisov, I did originally think it was Oumuamua was a comet. It was an asteroid. I was calling it an asteroid until I got told off by Alan Fitzsimmons, who told me that no, it's probably more like a fragment of a comet. Although I mean, it was an inactive one, a dead comet. That came through in 2017, I think, if I recall. And then last year we had Borisov.
Yeah, I think so.
In flying through the solar system as well. And that definitely was a comet. It had an atmosphere, a coma, and so on as well. Now, the reason they were flagged as being interstellar objects rather than objects in our solar system is because they were moving so quickly. Nothing in our solar system has any business moving that quickly. They're moving so fast that they will, escape the gravitational pull of the sun and leave the solar system entirely. Now, it's correct that that can happen within the solar system. So we think that most objects in the Oort cloud were probably ejected there by Jupiter, for example. Or Saturn, the major planets. Could it be something out there, as my father has hypothesized, that it was a binary object, two objects going around each other, and then a third object has come in and caused them to get flung, or one of them to get flung inwards, one maybe flung outwards. In principle, yeah, and actually that's probably why most comets that come inwards from the Oort cloud end up coming inwards, because they're sent in by some sort of encounter out in the Oort cloud. But these two objects are moving so quickly, so they're what's called their inbound velocity. Their velocity when they get out to infinity, out to way out of the sun's gravitational pull, is something like 30 kilometers a second. And nothing in the Oort cloud we know of can do that. They probably came from, well, if they didn't come from the Oort cloud, they came from another solar system. So if they came from that solar system, they probably got ejected by an encounter with a massive object. So if you do get a 3-body encounter, so you get maybe a binary system and a third thing comes in, and this works whether it's asteroids or stars or black holes or whatever, then the lightest of those 3 is almost always ejected at very high speed. You can think of that as if you think about sort of conservation momentum, you're going to have the same momentum given to each object, but the less massive one will have greater velocity, and so will be flung out. And so it's probably they were the small part of some sort of encounter, almost certainly in another solar system. I mean, we measure these if we think about comets coming into the Oort cloud, or comets get ejected from our solar system by say Jupiter. They have eccentricities, which is how elongated their orbit is, of about 1.01 or 1.03. So this is a measure of if that eccentricity is 1, they're on what's called a parabolic orbit. They will just escape. If the eccentricity is 0, they're a circle. So it gets longer and longer when you get out to 1, and then beyond 1, they're on these hyperbolic orbits. So comets are normally, if they're on that verge, normally at eccentricity about 1.03. These have eccentricities of 2 or 3, not 1.2
Oh wow!
or
So
1.2.
they are basically
really eccentric.
They kind of coming in and kind of just skimming, and then sailing off again.
Yeah, and it's a one-time pass. I mean, the estimates are that there's probably 1 a year of these objects, but they're so fast, you have to be able to spot them. And these all-sky surveys are good for doing that. They're also if they're things like Oumuamua, that was small. It was dark, so really hard to spot in your telescope as well.
So I guess to sum it up, it's because they're going too fast and they're just flying straight through us.
Yeah, it's not just that they're going too fast; they're going way too fast.
Yeah, way too quickly. So our second question comes from our good friend Mark de Vries. Mark Fridge, we like to say. We're asking all our guests this question. This is the thing that I'm letting all our little secrets out. All our little conversations that we have while we're recording, they're all going to come out because I can't keep a secret. So you're gonna get nice little tidbits. Anyway, the question is: Square Kilometre Array or JWST? Which is going to generate the most exciting science? And if each one could answer just one question about the universe, what would you like it to be?
That is a good. So these are 2 of the biggest projects coming online. I know you've spoken to Chris Lintott, who's outlined the projects already. So I don't need to go into too much detail. But I think if you look at their science goals, then what JWST, what the Webb is going to do is to look at the first stars in the universe, or the formation of the first stars, when that was and how that was. So we'll be able to see the first galaxies certainly with James Webb, just by looking at these longer wavelengths, looking at that redshift, that stretched light, and it will be able to take very high res images of other solar systems and potentially even other planets. But whereas SKA is going to obviously look at the radio waves. I was looking at you could think of this as what's the wavelength range? So what's the range of wavelengths? So JWST goes from about 6 microns down to 14 microns down to about 0.6 microns or something like that.
Yeah, something like that.
So that's what's that, a factor of, call it 20 in wavelength. Whereas the James Webb, whereas SKA goes, its wavelength range is a factor of 1,000.
Yeah.
Or more when it's up at well, certainly a few hundred up at when it's fully established. And so there's much more sort of parameter space to explore. The other thing about SKA, it feels to me like there's got more scope there for serendipitous discoveries, for discoveries of objects that we've never seen before. So we've got the things that we know we don't understand, that we want to know more about. So these fast radio bursts and so on that are blinding us every now and again. But there's likely to be other things out there that we've just never done. Square Kilometre Array is looking at such high resolution of bits of the spectrum we've just never seen in that kind of resolution before. In some senses, it feels to me, at least, maybe this is unfair, we know a little bit more what to expect with James Webb than we do with with SK. It's still going to do amazing science, and the questions it will answer are going to be amazing, and it will produce prettier pictures. There's no denying that. So in terms of what will get the press attention, and what will be in the news and all over the web, and no pun intended, will be James Webb. But the SKA, some of the science there, although potentially hard to visualize, looking at things like magnetic fields and the role of those in all sorts of things. It's a favored question of astronomers of considering magnetic fields, and have you considered the effect of that on whatever your science is.
Every seminar, it's like, have you considered magnetic fields? And everyone just goes, no.
Well, they're hard, and we don't really understand them that well.
Yeah.
Well, I mean, we understand magnetic fields. We've done that since Faraday's time, but we don't always understand their interactions with the interstellar medium, because they're hard to measure. You can't see the magnetic field. You have to look at its effect on other things. So you look at the way it normally the way it polarizes light, so the way it causes light to the wave to oscillate preferentially in one direction over the other. I'm doing the polarization dance there on screen, I realize. It'll oscillate in one direction or the other, preferentially. And so looking at that tells you a little bit about the magnetic fields. If that is rotated, so there's a nice thing called Faraday rotation, where as you change frequency, the amount that polarization changes with frequency tells you the strength of the magnetic field it's passed through. So no magnetic field, that polarization direction is the same at all wavelengths or all frequencies, but if there is a magnetic field, as you look at different frequencies, that kind of twists slightly.
Slightly being the key word.
Ever so slightly. You do need to know what's between you and the object you're looking at. So you need to know about how much gas there is there, how much ionized material there is there. That's something that's hard to not always easy to measure. But having much more detailed observations of this will allow us to study that in much more detail. And the other nice thing is that it can look at, if the processing is there, it can look at several things at once. So because it's this array of telescopes, certainly at the low frequency end, where the individual telescopes, rather than being at the high frequency end, they're dishes. They look like a radio dish. Whereas at the low frequency end, they're more like this pen.
It just like sticks out the ground, aren't they?
TV antenna. Well, it's not a TV antenna, it's a radio antenna. But it's a radio antenna stuck in the ground, or thousands of these things. And the nice thing about them is each antenna can see radio waves coming from all over the sky. But what happens is when you get, I have a second pen. I have a stylus and it's plastic wrapping still. When you get, which I was going to play with tonight, but I haven't had time yet. When you get a pen and a stylus, or two radio antennas, as we'll pretend they are, and you combine their signals in the right way, then you can actually start to look in specific directions. And that's all done through just by the time difference. If a radio wave comes in from over here, it hits that detector slightly before it hits that detector. So you look at the timing between the two. And the nice thing is, if you store all the data, you can sit there and change those times. You can store the data. You can apply different time differences, and actually look. One time difference will let you look over there, another time difference over there, another time difference over there. Now, the catch is that's a lot of data. These things produce a lot of data. Yeah. But it does have the potential that you could say, well, if we've got that, then if we know, for example, it's a fast radio burst we want to study, well, let's point one of our directions at that and sit there and wait, and then do some other stuff. Maybe not at that for 24 hours a day, but you could dedicate some stuff. You could do much more targeted approaches than you can with a normal telescope, if you've got the power and the processing to do that.
So I think the answer is SKA that you're most excited about, maybe.
I think because of the serendipity, because of the unknownness. That's not a word. It is now. Of the
anything goes on
science it's going to do.
Awesome. Thank you so much for answering the questions. It was great about the SKA, like stuff that I didn't really know or / had forgotten. So yeah, thank you so much, Chris.
No problem.
And the people teaching you.
Sorry? The people teaching you.
She didn't know. I blame the people teaching it.
Yeah.
Well, thanks very much, Chris. It's been an absolute pleasure speaking with you.